Hello everyone. In today's lecture, we'll be discussing the principle of separation. This is a very important method in control algorithm design. And the principle states that if the system is controllable and observable, the design of the state feedback control and observer can be done separately without affecting the overall performance of the combined system. Once both the methods are combined, the system stability can be guaranteed. Uh, this method actually simplifies the control design process in the control system implementation. In this direction, in this lecture, we'll having the mathematical modeling of the separation principle, how we can implement for the observer and state feedback control. We'll come up the system dynamic model. And in next few lecture, we'll have the examples, how we can implement this method for practical problems. Then we'll conclude this part of state feedback control and observer design for a system. Then we'll come up the new topic, optimal control algorithm. As I mentioned, the separation principle basically, this is basically combined system stability analysis, where we'll combine both the state feedback control and observer together to improve the system stability. It is actually simplifies the control system algorithm. So let's start the mathematical analysis of the separation principle. So here we are going to assume the tracking problem. So in that direction, we'll assume xt not equal to 0. And based on that, we can design the control algorithm. The control algorithm will be equal to a x dgr minus x naught estimated state minus the feed forward control xt. So where xt is the desired state vector and x naught is the estimated state vector and is the feedback gain matrix and kd is the feed forward gain matrix. The system, we are assuming the original system model x not equal to ax plus bu, y equal to cx plus du. And the observer part, what you have done before observer, if you remember, this is already you have done. Observer equation we had x naught dot equal to E minus LC x naught plus B minus LD U plus LY. Now let us define this, the equation number 1. This is equation number 2. Now if you substitute the control input here in the equation 2, our observer dynamics yields to be x naught dot equal to A minus LC x naught plus B minus LD. In place of U, we can write kxt minus kx naught minus kd xt plus ly. And if we write further, A minus LC, we can write x naught plus B k xt minus bk x naught minus b kd xt minus l d k xt plus l d k x naught minus plus l d k d xt plus ly equal to, so you can further simplify a minus lc minus bk plus ldk x naught plus bk plus bk minus bkd minus ldk plus ld kd plus ly, or we can write, so here xt term are missing into xt, bracket into xt. So further we can write a minus lc minus bk plus ldk into x naught plus b into a minus kd minus ld k minus kd xt plus ly, or we can write a minus lc, or you can write a minus lc minus bk plus ldk x naught plus b minus ld into a minus kd xt plus ly. Right, we can write this. Also, we know that the output equation from the original system, cx plus du, right? Now, if you substitute this equation y in, let us define the equation number 3. Now, if you substitute y here in place of y in the equation 3, we can write x naught dot equal to a minus lc minus bk plus ldk into x naught plus b minus ld into k minus kd xt plus lcx. So we just multiplying L with this output equation. So lcx plus ldk xt minus ldk x naught minus ld kd xt. And if you note, also you can write this expression. If you further expand this equation, a minus lc minus bk plus ldk into x naught plus bk xt minus b kd xt minus ldk xt plus LD KD XT plus LCX plus LD KXT minus LD KX0 minus LD KD XT. Now, if you notice here, there are some terms we can cancel. So here we can cancel LDK X0, LDK X0, we can cancel this term, and LDK XT, we can cancel this term. I think another term also we can cancel. Yeah, LDKD XT, this term also we can cancel, right? So from this, we can write, after cancelling those terms, we are having A minus LC minus BK into X0 plus B K minus KD XT plus LCX. Yeah, this is the expression we are having. And let us define this, the equation number 4. Okay. Also, we have the Plant equation. From the Plant equation, if you substitute the control equation, so from the Plant equation, we can also write Plant state equation. So we are designing, this is the observer part. Now we are working with the state feedback control part. So we have the X dot equal to AX plus BU. So in place of U, we can write our control equation, what we had. This is our control equation, we can substitute there in the plant dynamics. Then we'll have the augmented system with control, basically state feedback control, we can say. So we can write AX plus B into K X TGR minus K X0 estimate state minus KD XT. Is the last term actually feed forward control part. And from this you can write AX minus B K X0 plus B K minus KD XT. And let us define this equation number 5. Now writing equation 4 and 5 in compact form or in matrix form, we can write equations 4 and 5 in matrix form. We can write X dot. If you notice here carefully, we have here the coefficient, sorry, the states are X0, XT, X, here also X, X0, XT. So we can write in matrix form, equation 4 and 5, X dot, X0 dot equal to, we can write A minus BK LC, A minus LC minus BK, and the state vector is X0 plus the control term here. We have B part here. This is one B part is here, another B part, the term of the B matrix here, right? So you can write B into K minus KD and B into K minus KD. And this is XD. So here, this is the closed loop control system. So for this, we can denote as this is ACL, this is B here, right? Here, if you notice carefully, the order of this closed loop system, the order of the above system, we have 2n, because for the first row, for the x dot is n, and for x dot also n. So 2n we can write. Also, if you notice here, the input is the basically here xd. xd is the input. So if you write this equation ACL x, BCL xd, so xd can be considered as input to this combined system. Now let us find the error dynamics. So we have the combined state feedback equation and also observer. So now we'll come up the error equation for this system. So let's write. Assume estimation error E naught equal to x minus x naught. And now the x dot equation we can write based on this aerodynamics. The equation we have equation 5. The equation 5 yields to be x dot equal to ax minus bk x naught plus bk kd x to z. So here in this equation, we will take the error part in this equation. For this, we are adding and subtracting bkx to the x dot equation. We can write x dot equal to ax minus bk x naught plus b k minus kd xd plus bkx minus bkx. Okay, so from this we can write a minus bk into x plus bk x minus x naught plus bk minus kd x dz. Okay. Now this here we can write x minus x naught as e naught. Right. This is already have defined here. X minus x naught e naught. So we can write a minus bk x plus bk e naught plus b into kd x dz. Okay, and let us define. Okay, this is equation number 6, and let us this equation number 7. Okay, now if you subtract equation x dot dynamics, so x dot dynamics we have here equation 4. From equation 7 we can write now subtracting equation 5, equation 5 from equation 7, we have x dot minus x naught dot. So we are finding the error dynamics now. A minus bk into x plus bk x minus x naught plus b into k minus kd xt minus a minus lc minus bk into x naught minus b k minus kd xt minus lcx. So here, if you notice, this two term can be cancelled. This term and this term. So now the equation yields to be ax minus bkx minus bkx naught bkx naught, I can write as plus bkx minus bk x naught minus ax naught minus plus lcx naught plus bk x naught minus lcx. So here also you can cancel some term. So here we can cancel bkx, this one we can cancel, and we can also cancel bx naught and bx naught, bkx naught. X naught can cancel. So from this also you can write equal to, you can write ax minus x naught minus lc x minus x naught. Okay, from this also you can write a minus lc x minus x naught. This is also you can write a minus lc e naught. So this is what we had before. If you remember, this is the aerodynamics from the state equation and observer we had. So let us define this equation number 8. Okay. Now, let's find the tracking error dynamics. This is the E naught is the observer dynamics. Now, if you find the tracking error dynamics, you can easily find. So here, tracking error. So now we are going to find E and E naught. So our main aim is E and E naught, E dot and E naught dot. This is our main. So error in the x minus xt and x naught dot. Okay, this is our E naught dot basically. So tracking error. Error E can be written as E equal to xt minus x. And xt dot, we know AD xt. So this is the desired dynamics. So here, please remember that the eigenvalues of AD are negative. So this is the system we'd like to follow, that controller should follow xt dynamics, right? So from this we can write, E dot equal to xt dot minus x dot. So from this we can write AD xt minus x dot. And x dot we know, x dot already we had. x dot already had, so x dot was defined in equation 7. So we can substitute here. You can substitute AD xt minus A minus BK x minus BK E naught minus B into K minus KD xt, right? So from this we can write AD xt minus AX plus BKX minus BK E naught minus BK xt and plus BKD xt. Now here we are adding and subtracting from both. This is defined equation 9. So now we are adding and subtracting AXD to the equation in the right hand side of equation 9. So adding and subtracting AXT on RHS right hand side of equation 9. We have E dot equal to A dxt minus AX plus BK x minus BK E naught minus BK xt plus BKD xt plus AXT minus AXT. So this equation we can further write A xt minus x minus BK xt minus x plus AD xt plus BKD xt minus AXT minus BK E naught. Okay, minus BK E naught. And further we can write this equation A minus BK into, so from these two terms we can write, from these two terms we can write A minus BK into E xd minus x is E, already we have defined. This is already defined. So E plus AD minus A plus BKD xt minus BK E naught. Okay. So here, this is, let us define this equation 10. Okay. Now, if you combine equation 10 and equation already have. So equation also basically our dot. Now, if you combine equation 8 and 10, so in matrix form, of equation 8 and 10, we can write E dot E naught dot equal to A minus BK minus BK 0 A minus LC and the coefficient of, these are the matrix comes out from coefficient E and E naught, the steady vector, plus we can write AD minus A plus BKD 0. And because if you do the equation 8, there is no xt term there, so xt 0, so xt you can write. And let's write this is closed loop matrix augmented system ACL, and this is BCL. Let's denote BCL. Okay, so you can easily see from equation, this equation 11, that for the estimation error, here if you would like to estimation error E naught to 0, all eigenvalues of A minus LC must be negative, must be left half plane. And for tracking error, this is the tracking error and this is the estimation error. This is estimation error and this is the tracking error. And tracking error, for tracking error to 0, all eigenvalues of A minus BK must be in the left hand plane. And so this the condition should be validated. Along with this, there is another condition. It should satisfy this part. So this part also to be 0. So we can write. So the point is, if E is going to 0, the eigenvalues A minus BK should be negative, all negative, and for E dot to 0, the eigenvalues of A minus LC to be negative. Eigenvalues of this should lie in the left hand plane. And along with this condition, this part to be 0 also. So we can write along with the above condition, AD minus A plus BKD to be 0. So how it can be 0? So we have to make KD in such a way that AD minus A plus BKD to be 0. So I can write here KD should be selected in such a way that all elements of AD minus A plus BKD equal to 0. So this is how we can do the combined analysis of the estimator and observer together. And this is how the separation principle is designed for a system. And here also we have taken the critical cases like xt not equal to 0. Also we have used feed forward control. But if the xd is not equal to 0, if it is a regulator case, the problem will be more simplified. And even if there is no feed forward control, it will be more simple. Problem can be defined in more simplified form. So we have taken the critical cases here in this design. So we'll validate this analysis example in the next lecture. Thank you.